Let us start today's class. It is the next theorem, which is in the network theorem. We have studied Thevenin's theorem in the last class. Now we will be studying Norton's theorem. So today we will be seeing Norton's theorem and Norton equivalent circuit. So what is Norton theorem? What does it state? So how we can state that it is possible to simplify any linear circuit, any resistive circuit, no matter how complex it is, you can simplify it into an equivalent circuit with just a single current source and parallel to that current source just a resistance, and then it is connected to the load. So we can reduce it as simple as one current source, one resistance which is parallel to the current source, and it is connected to the load resistance, as we can see in the right hand side figure. You can see here IN is the current source and ZN is the resistance connected parallel to the current source, and these two is connected to the load resistance. So this is the Norton equivalent circuit. So any complex circuit you can reduce into this form as shown in this figure. So how can you convert it? How will you find the values of IN and ZN? Here you can see in the left hand side picture the Thevenin equivalent circuit. This we have already studied. Any linear complex circuit you can simplify it into this form with the one voltage source in series with the one resistance, and both connected to the load resistance. And this is also a simple equivalent circuit of a complex resistive network. In the same way we have done with the current source as here in the Norton equivalent circuit. In both cases you can see the resistance ZTH and ZN both are same. So ZN should be equal to ZTH, and the voltage ETH is equal to or it is connected to the value IN with this formula, which is IN is equal to ETH by ZTH. Okay. So this is the voltage source with resistance, which is Thevenin's equivalent circuit, and current source with the parallel resistance, which is Norton equivalent circuit. So we can simplify any linear complex circuit into these forms using the Thevenin's theorem and Norton's theorem. So now let us see what is the value of current I2 in Thevenin circuit in the load ZL. So let us see Thevenin circuit, and we are going to find the value of current I2 passing through the load resistance ZL. So what will be the value? It will be ETH divided by the total voltage. So here left hand side figure, that is also ETH, isn't it? You see here in this picture the voltage source is denoted with E there. That is not correct. It is ETH. Okay. And the right hand side along the ZL, it is not ETH. You have to correct it. I will do correction and I will send it to you. Okay. ETH is not there. ETH should be with the voltage source. Okay. Left hand side with the voltage source you have to correct E. Instead of E you have to write ETH. Okay. Then I2 is equal to, it is the current passing through the load resistance, which is ETH divided by the total voltage is distributed to both resistance ZTH and ZL. So ETH divided by ZTH plus ZL. That will be the current, the total current passing through the circuit, which is I2. And now this is equation 6. The current IL in Norton circuit in load ZL. Let us see how will you find the value of current IL passing through the load resistance. It is IN into ZN divided by ZN plus ZL. See that it is IN into ZN by ZN plus ZL. That is the current passing through the the ZL resistance, load resistance. That means you can see that we know that it is Zn which is equal to Zth. So let us substitute that Zth instead of Zn, and In we know that it is Eth by Zth. There that also we have to substitute in equation 7. So we have to substitute Zn and In in equation 7. Then IL will be equal to ETH by ZTH plus ZL. That means IL is equal to I2. That means current passing through the load resistance in Norton's equivalent circuit and Thevenin equivalent circuit both are equal. Understood? So this is the theory behind the Norton equivalent circuit. Understood? Okay, now next we go to again the theorem is written here. The Norton equivalent circuit contains an independent current source which is parallel to the Norton equivalent resistance Zn. It can be derived from the Thevenin equivalent circuit by using source transformation. Therefore, the Norton current is equivalent to the short circuit current at the terminal being studied. So Norton current is equivalent to the short circuit current at the terminal being studied. So it is when you short circuit the current at the terminal at the equivalent. So here Norton current is equivalent to the short circuit current at the terminal. So at the terminal if you short circuit it will be equal to the Norton current. And Norton resistance is equivalent to Thevenin's resistance. So this is Norton's theorem. And let us see with an example. So derive the Thevenin and Norton equivalent circuit of below figure. Here the same figure is shown as we did for Thevenin circuit. The voltage source and current source are there. Resistance are also the same as we did for the earlier case. What we should do is we know that ETH earlier we have found out that it is ETH is 32 volt. You can see here ETH was 32 volt here and ZTH was 8 ohm there. So that is what we are going to take. So ETH is 32 volt, ZTH is 8 ohm as we did in the previous example. So IN will be 4 ampere. So Thevenin equivalent circuit is shown here. And what will be the Norton equivalent circuit there? It will be 4 ampere current source and 8 ohm resistance is parallel to the current source. This will be Norton equivalent circuit. You have to do one more example which is in the textbook. You just check in the textbook. I will later I will do it in the PowerPoint. Maybe later I will do it in the PowerPoint or write it in my notebook and take the photo and send it to you. Okay. Otherwise you can just check it in your textbook. I will send that textbook photos also. So now next we go to maximum power transfer theorem. So how will you study? How will you understand what is maximum power transfer theorem? This means this theorem says that maximum power will be delivered to a load by a generator. Generator can be voltage or current generator. So maximum power will be delivered to a load by a generator when resistive when will this maximum power will be delivered? You can see two cases. When the resistive components of the impedance of load and generator are equal. That is resistive components of the impedance of load and generator. So ZL and the resistive components of the generator, the resistance of the voltage source or the current source should be equal, and the reactive components of the impedance of generator and load are equal in magnitude but opposite in sign. So we need to check what is resistive components and what are reactive components of the impedance. Let us see that. Then you will understand it clearly. So if we have total impedance of a circuit, let it be Z prime. So if a circuit has a resistance Z prime it can have complex component and real component. So it can be in complex nature, in imaginary component and real component. So the resistance can be complex. So Z prime, let it be equal to R prime plus J X prime. So X prime is the imaginary part there, R prime is the real part. And its load resistance, load impedance, let it be ZL. So it can also have real part and imaginary part. It is also complex in nature. So it is equal to R plus J into XL. Okay. So now the see here, now this is the circuit. E prime is the voltage coming from the voltage source, and Z prime is the resistance connected in series with the voltage source, and ZL is the load resistance. Now let us see the current passing through this ZL and Z prime. So that is equal to E prime by Z prime plus ZL. Okay, and now let us write in the terms of real and imaginary parts. Z prime is equal to R prime plus Jx prime, and ZL is equal to RL plus JXL. So let us write that, and real parts are added together, and imaginary parts are added together, and you can see that it is equal to E by R plus RL plus J into X plus XL. Understood? Now power delivered to the load. Let us see the power delivered. The current passing through ZL is I. So power delivered will be I squared RL. I squared RL. Now let us substitute for I. Then you will get power is equal to, sorry, left hand side will be P instead of I there. P is equal to E squared RL, E prime square RL divided by R plus RL whole square plus X plus XL whole square. I square will be denominator whole square, and it will be X plus I, A plus IB form. So the its square is its modulus square. So A square plus B square will be the square of A plus IB square. So that is what written here, R prime plus RL whole square plus X prime plus XL whole square. So that is the square of R prime plus RL plus J into X prime plus XL. Okay, now we need to take the derivative of the power with respect to XL. So let us take the derivative. Why do we take this derivative? Because we need to find the maximum value of power. So when you have a power equation, if you want to find its maximum or minimum value, then you need to just do the derivative of the of that value, that power, with respect to the variable, which is XL or RL here. So we are taking first with the XL, dou P by dou XL. That will be, derivative will be equal to 0. So let us do that. Dou P by dou XL, which is equal to 2E prime square into RL into X plus XL divided by R plus RL whole square plus X plus XL whole square, the whole square. So it is product rule. We are taking, denominator is having the variable, so it will be denominator 1 by denominator whole square into then derivative of the X plus XL whole square, that is 2 into X plus XL. So that is what we get. So this is equal to 0, and when we take this will be 0. This 0 means the numerator is equal to 0, isn't it? So numerator 0 means X is equal to, X plus XL is 0, that is X is equal to, X prime is equal to minus XL, or XL is equal to minus X prime. So this means this is what the second case says here in the maximum power transfer theorem. The second case says that the reactive components of the impedance of the generator and load are equal in magnitude but opposite in sign. That is what we have found out. XL is equal to minus X, equal in magnitude but opposite in sign. That is, if XL is inductive, if you have inductive reactance there in the load resistance, then the X prime, the resistance in series with the voltage source X prime should be capacitive, and they should be equal in magnitude. Opposite in sign means it is if inductive, that the other one should be capacitive. That is what it represents, the opposite in sign. Now let us write now the after substituting XL is equal to minus X prime in the power equation. We have the equation for power, which is P is equal to E prime square RL divided by R plus RL whole square plus X prime plus XL whole square. So let us substitute for XL there as X prime minus X prime. So P max will be E square RL, E prime square RL divided by R prime square plus RL square. The second term in the denominator is 0. So we get the maximum power. Now considering the variation of P max with RL. So now RL is varying. We have taken the derivative with respect to XL already. Now we have to take the derivative of power with respect to RL. So let us take the new power equation. Let us take the derivative with respect to XL. Then dou P max by dou XL is equal to 0. So taking the derivative with respect to XL, it should be 0 when this is done in order to find the maximum value of P max. Okay, so dou P max by dou XL, let us find. It is E squared RL into minus 2 into RL plus R prime raised to minus 3 plus E prime square divided by RL plus R prime square. Okay, it is as a product. So first into derivative of the second plus second into derivative of the first. Here we have taken E prime square RL as the first term and second term as 1 by R prime plus RL whole square. So E prime square into E prime square RL, that is the first term, into derivative of the second, which is minus 2 into RL plus R prime whole raised to minus 3 plus second into E prime divided by E prime square divided by RL plus R prime square into derivative of RL, which is 1. So that is what written there. Now equating this to 0, you will get and taking the common denominator, you will get E prime square into RL plus R prime minus 2 E prime square RL is equal to 0 divided by R plus RL whole cube is equal to 0. See, common denominator, we have taken only common denominator there. The numerator is equal to 0. Let us see. E prime square into RL plus R is equal to 2 E prime square RL. If the denominator goes to 0, so the numerator is equal to 0. Denominator goes to right hand side, so it will be equal to 0. Right hand side becomes 0. So numerator is equal to 0, that is E prime square into RL plus R prime is equal to 2 E prime square into RL. And this in turn gives RL plus R is equal to 2 RL. E prime square get cancelled. This means R prime is equal to RL. Isn't it? R prime is equal to RL. RL plus R prime is equal to 2 RL means RL is equal to R prime. So the maximum power will be delivered to the load when the resistive components of generator and load are equal. So the first condition is satisfied. Resistive components of the impedance of load and generator are equal. So this is what we got in this equation. So now let us substitute R prime as RL in the previous equation for power max. P max is equal to E prime square into RL divided by R prime is RL is, so 2RL whole square. That means E prime squared by 4RL RL square. RL get cancelled, so 1 RL get cancelled. So E prime square divided by 4RL will be the maximum power. Okay, so this network theorem is finished. One example of Norton equivalent circuit, one problem I will do it and send it to you. Okay, you have to do these problems, other problems which is given in the back side of the chapter. There is exercises, so there are many exercises you can do it, and if you don't find the answer, or if you have any difficulty in finding the answer, I just call me or just send me the problem. I will try to do and send it to you. Okay.